Okay, so let us start with the fourth lecture by Pierfrancesco Urbani. And if you have questions, please just do it. But if you remember, use the microphone. We always forget that, but...
Okay. I can do it. Okay, so yes, so the idea of today is just to tell you what's the structure of the line of reasoning that we use to get to these values of the critical exponents of jamming. So I think that we stopped yesterday in the middle of a computation, so I would like just to make a kind of recap of what we have said in the last days. So we started from the packing problem. And then we said, okay, so this is a constraint satisfaction problem in which we would like just to pack spheres as close as possible in such a way that do not overlap. And then we said, okay, let's take some abstract point of view and transform this into an abstract constraint satisfaction problem with continuous variables. And we consider this perceptron, which is a model coming from machine learning, in which we have this variable W, which contains our degrees of freedom. So this is an n-dimensional vector. And it lies on the hypersphere. And then we said, okay, let's define some gap variables analogous to the gap between pairs of spheres that are defined using some set of random vectors. So each vector is an n-dimensional vector with components that are Gaussian variables. And then we say that the gap is like this. And then we have a control parameter sigma that plays exactly the same role as the sum of the radii of different spheres. And we have m random vectors and m scales with the system size, with n. So I have n degrees of freedom and m constraints, and m scales with n. And then the continuous constraint satisfaction problem is just to find an assignment of W such that all the h mu are positive. Okay, so this is true for all mu. Okay, and then we would like to identify the jamming point as the point where I'm not able to find an assignment for those variables that satisfy those constraints anymore. Okay. Okay, so what we discussed yesterday is that if we want to study this problem, what we can do is to compute a free energy where Z is just a partition function. And this Hamiltonian is just some cost function that penalizes gaps that are negative. So we can choose, for example, the harmonic cost function in analogy with harmonic spheres. So we say that this is sum over mu over up to m, so over all the gaps. And then we say, okay, we pay energy that is quadratic only when the gap is negative. Okay? So this is really analogous to harmonics of spheres, except that we replace the form of these gap variables by these ones. Okay? And then we argued that if we are able to compute this thing, we can get access to the full phase diagram of the model, and in particular, the point in which you are not able to find a solution anymore, which is the Jammine point. And then what we did is that we started the computation of this free energy, and then we used the replica method to average over this log. So we said, okay, the log of Z, I can write it as the limit as small n replicas are going to 0. Oops. And then we use the fact that we are able to compute this average when small n is integer, because this corresponds to having small n integrals over small n replicas of this vector W. And then we arrive to the point in which Z to the n averaged, this is an integral over some order parameter, which is a matrix, small n by small n matrix, Q, exponential of n times some action of Q. Okay? And then we said, okay, if we want to compute this and then get the free energy, we just need to compute this integral. But now you see that this object does not depend on n. And so when n is large, we can compute this integral by a saddle point. Okay? So the action S of Q can be written as 1/2 log that of Q plus alpha log of some impurity partition function. This is just a single body, single degree of freedom partition function. And then we ended up the session yesterday just with the computation of this term. Okay? And this depends, of course, on Q. Okay, so just as a recap, the meaning of this matrix Q is that, so if I look at its elements, those give me the typical distance between two different replicas in the system. So if I take if I extract with the Boltzmann measure two configurations W, both subjected to the same disorder, so to the same set of random vectors xi mu, then their similarity is encoded in this matrix. Okay? And in particular, if I'm able to compute this, so when n is going to 0, this matrix is parameterized by a function, Q of x, which is a function, okay, mathematician write something like this, I guess. And then if you look at this and you look at its inverse function, x of q, this gives the probability distribution, actually, the derivative of x of q with respect to q gives the probability that if I extract two replicas with a Gibbs measure, they have an overlap q. They are at distance q. And I measure the distance by the scalar product of these two vectors. So you need to think at this, if you have in mind glasses, as q being morally the mean square displacement between two configurations of the particles. It's just a measure of the distance in phase space of two configurations of the system. So if I look at particle systems, instead of having x of q, I will have an x of delta, and then I can compute p of delta. Okay? So in these ansatz, in the ansatz in which you have this structure for QAB described by this function, you encode essentially all the structure in phase space of solution of your problem. Okay? And then what we did is that we plugged these ansatz inside this term, and we wrote down a partial differential equation to compute this term. So this term becomes, so, okay, here I need to write a bit. So it's a Gaussian integral. Okay, it's Q0. Sorry, it's Q0, not 1 minus Q0. I'm sorry, I apologize. And then there is this f of 0 and, okay, sorry. And let me write here h. And this f is the one that was satisfying this partial differential equation that we wrote. Oops. So it's a nonlinear partial differential equation which must be integrated backward in this time index x with this initial condition. And here it's just the local potential that I have there. Yes.
Can you just come back to the Q equals or equivalent to a delta? Mm-hmm. You mentioned that this equality would be when I go to the particle systems. Can you repeat it again?
Okay, so in this setting, the degrees of freedom are the W's, right? And when we made this moral mapping between this problem and the Jammine problem in spheres, morally, the degrees of freedom that in sphere system must be compared to the W's are just the position of the particles. These are my degrees of freedom. And then this thing is just a measure of similarity between two different positions in phase space and how much those two positions are close to the other. And here, in particle systems, a measure of similarity is just a mean-square displacement. So it's just 1 over n.
Okay, yeah. Okay.
So if I have two replicas, it's just this. Square.
Yeah, right. I understand. Yes.
Okay.
Thank you.
Yes, Jim. Mm-hmm.
If I had a big, are you assuming now that you're dense enough so that you're looking at rattling in one cage or something? Because otherwise, every 2 times you make the glass, you would get the very big displacement.
Yeah. So, okay. So that's the reason why the derivation that I decided to do was not for particle systems.
Yes.
Because in particle systems, you know that if I look at what I was calling the Franz-Parisi potential, you always have a yeah, so I'm considering just being here, which means that I have a glass, I cannot diffuse away, so I'm inside a meta basin, and then I look at what happens when I compress this glass, for example. So I have a colloidal glass, it's caged, and then I look at what happens with the pressure. So if I just rewrite down the phase diagram, so I have this is the liquid or gas phase because you don't have attraction, as you discussed. And then here I pick a glass. So I'm here. I do not see this minimum because I see it only on exponential timescales. So I forget about this minimum. I look at the thermodynamics of a glass. And then I look at what happens when I compress. And then when I compress, at some point, I get this Gardner transition. And when I get this Gardner transition, the order parameter is not just the cage, but you have a cage, a series of cages that describes the structure of free energy within a glass. So when you hit this point, here your order parameter will be something that is a function, delta of x. And x is this parameter that tells you where you are in this free energy landscape.
And this is one of the reasons why you're not doing the big problems that you're doing.
Exactly. So, I mean, in order to discuss this, I need to discuss this thing. This thing has no quench disorder, but you have engineered the system in order to have it because there is a reference configuration. And then you need to do the large dimensional limit of all this. And this is complicated. So the reason why I decided to do the perceptron is just that it's much simpler, somehow. And in the end, it's a bit faster to go close to Jammine. Okay? So you avoid a lot of technical things that are due to the fact that you are dealing with particles. You need to use field theory. There is no quench disorder, and so on. So here there is no field theory. There is no density functional theory. So I can just do some disordered system computation. Okay. Okay, so we reduced the problem of computing this free energy that in particle systems would be the analogous of the Franz-Parisi free energy. Here it's just a free energy. And in order to compute this free energy, we need to solve this partial differential equation. Now, this partial differential equation depends on this order parameter, Q of x. Okay, so if I give you Q of x, you solve this, you plug it here, and then you get your free energy. Okay, but now we need to find Q of x. So we have free energy, which is a functional of this function here. And then we need to take the saddle point with respect to this Q of x. Is it clear? So it's like having the free energy as a function of the magnetization. What you need to do is that you need to look at the minimum free energy as a function of the magnetization. Here, the role played by the magnetization is just this function Q of x. Okay? So the logic of the problem is always the same. It's just that here we have this complicated order parameter. And now you see that you have a problem. Why? Because when you try to do the optimization of this function with respect to Q of x, you need to impose that this term here that you compute this way depends on this f, and f is constrained to satisfy this equation. So you have a constrained optimization problem, because you are not allowed to vary all your parameters as you want, but you need to, when you vary your order parameter, you need to take into account that this produces a change in your function f, which enters here. So it's a very complicated problem. So how do you do constraint optimization problem? What you do is that you introduce Lagrange multipliers, right? So in principle, I have this term here. So I didn't tell you how this term is computed, and I will not, because it's long. And this is not very, very important. So what you do is that you say, OK, now let me free this function f. Let me assume that this is like an order parameter itself. And then let me introduce two Lagrange multipliers. And those Lagrange multipliers have to be functions, because I want to fix f that satisfies this equation for each x and h. So what I do is that I add to this action Lagrange multipliers. Is the line of reasoning clear? Okay. Well, good. So what you do is that you say, I want to fix this equation, then let me add to this action. So, and now I need to be sure that okay. Okay, whatever constant I put here, it's not very important. It's just a redefinition of the Lagrange multiplier. And then here I put just the equation. Okay? So this is a Lagrange multiplier that for each x and h enforces that this thing is equal to 0. Okay? So this is just constrained optimization, the mechanics 101. And then, so this enforces this, but I need also to enforce the initial condition for the partial differential equation. So I need to add something. Now, x is equal to 1, so I just have an integral over h, because this thing is just a function of h. And then here I have f of 1 and h minus log of blah, blah, blah. Okay? Is the structure clear? It's the same alpha. I mean, if here I can put whatever I want. It's the same?
P is continuous at 0.
Yes. So if you put the same alpha, you get something, I mean, you get that this when x goes to 1 is exactly this. If you do something else, you get something else, but I mean, it's better to do this way. And actually, this is important because P will be a probability distribution if you use this. You can, here you can do whatever you want. If you don't flip the sign, then you know that this is mine. So when P of x, when x is going to 1, then this is minus what you put here. I mean, when you take the variational equation. I mean, for the moment, this is just a trick. So I can do whatever I want. And then I just do it in such a way that in the end I get some simple formulas. But here, really, I can do whatever I want. Okay? So now I have an action, which is a function of q of x. It's a function of this function here and this function here. And now I do the variational problem with respect to everything, as you do in constraint optimization. So if I just take the variational equation with respect to P and P, I just get back these two equations, right? But then I can do the variation with respect to F. Okay? And this gives me another set of equations that I just write. I will not derive the two. But it's just a simple, you just need to write the Euler-Lagrange equations for this field. And you get the following equations. So you get P dot of x and h, that is q dot over 2, P double prime, minus 2x P f prime prime. So it's another PDE. And now this PDE must be integrated with an initial condition that is in 0. And this is just a Gaussian. Okay? So the way in which you can get this is that you take the action, that is this term plus this, and then you take the variational equation with respect to the function f. Okay? And for each x and h, this will give you this equation here. And then you have a boundary term that will give you this initial condition. So now you see that you start to have two PDEs, one that is going backward in time, because it starts from x equal to 1, and you want this function at x equal to 0. And then the other one that is going forward in time, from 0, and I would like to integrate it up to x equal 1. Now, both of them depend on q of x. So there is a missing equation that I need to find in order to fix q of x. And if I get it, then I have a closed system of equations that I can solve. Those are my mean field equations for the free energy. They play exactly the same role as m equal to tan h of m something, plus something. Okay? In a Q-revised model. So they are just the mean field equation for my order parameter, which is this function q of x. Now, what is the last equation for q of x? Okay, I just write it, and I don't derive it, but you will believe me. Okay, so this thing you get when you derive the action with respect to f, and now I can take the derivative with respect to q of x. And if I do it, I get something like this. And then here I have some function that now I don't remember. That's bad. And here you have a function that I need to properly define. But so you get something like this, and we will never use this equation, so it's not very important. So if you just work out the detail of taking the derivative with respect to q of x, you get those functions here. And they come from this term that I didn't write, but you can get it, there is a way to get it, so it's not very important. So, okay, so these are the mean field equations for the order parameter that is this function q of x. Now, in principle, if you are able to solve those equations, you get access to the full phase diagram. Okay? Now, what I would like to tell you now is how we can get information on just the jamming point. So, So let me just rewrite the phase diagram of this model. So I have two control parameters, alpha, that is roughly the packing fraction in my problem, and sigma, that is like the diameter of my particles. And I have here at high density an unsat phase, where the energy is positive, and a SAT phase where the energy is equal to 0. So if you think in terms of spheres, in these regions, the system is like jammed, so spheres overlap. And here, I'm able to get the spheres at 0 overlap. And there is a line that is a jamming line that separates the SAT phase from the unsat phase. Now, what I would like to do is to study those equations when I reach this line from below. So I'm in the liquid or the glass phase of our spheres. Those are spheres are at finite pressure. And then I want to squeeze them up to the jamming point where the pressure diverges. Okay. So what should I expect when I go towards this point? Now, if I go towards this point, what happens is that, so let me just think about spheres for a moment, which is a bit simpler to imagine. So I am in a glass. So spheres just rattle. And on short time scales, they rattle inside a cage which is delta, I call this cage delta EA. And EA stands for Edwards-Anderson. And then if I wait long enough, the system will age. And then the effective cage will be bigger. So if I think in terms of dynamics, so I can look, for example, at the mean-square displacement as a function of time. So I start from a typical configuration of the glass at time 0, and then I look at how far I go when I increase the time. Okay? So you see that this object is like a two-replica object. You have one replica at time 0 and one replica at time t. Now, this thing, what does it do? It does, in the glass phase, you get just something like this. Okay? And this thing is what I call delta EA. But so if I allow the time to be very large, what you can show is that this actually starts to drift very, very slowly. Okay? And this drift is what describes this function delta of x that is analogous to q of x. Okay? So it's like if I have a hierarchy of cages. So on short time scales, I just explore this smaller cage. And then if I have more time, maybe I'm able to look for some position where I can expand and vibrate more, and I expand the cage. So there is a short time cage size. That is what I call delta EA. But this is just the one in which the one that I see on short time scales. If I'm allowed to explore the phase on longer time scales, I can realize that I can move a bit more away, and so the effective cage can increase. And this effective cage is precisely described by this function delta of x that is analogous to q of x in our case. So in our case, so we can look at the analogous of this is just the correlation function that you can define as like this. And now if you just write down the same thing for this, So just the analogous object for delta of t. So if I just look at c of t and 0, so at equal time, sorry. Let me just do the scalar product. Just because the scalar product is the overlap, right? So if I do the scalar product at initial time, this is 1, because W lives on the sphere. So I start from 1, and then I go down, because I start to decorrelate from my initial position, and then I get to a plateau. And this is what I call QEA. And again, EA stands for Edwards-Anderson. So this is sometimes called the Biwaller factor. Okay? And now, if I have more time to explore the phase space, I can imagine that this starts to go a little bit down this value, and then I explore this Q of x. So, okay, this I can erase. So what is the interpretation of this with respect to the mean field equation? So I have this function Q of x, which has a shape like this when you integrate the equations. So you have a plateau here whose height is just QEA. So I land here on short time scales. And this is described by this thing. And then when I'm able to explore a little bit the phase space, I start to see all this structure here. Now imagine that I go to jamming. So if I go to jamming, at some point, the space that I can explore is 0, which means that this plateau value, QEA, is going to 1. Because if it is going to 1, I'm blocked at the initial position. So if I start my dynamics exactly at jamming, this will never move. Okay? So this means that this plateau is going to 1. Okay? Is it clear? Yes?
I didn't understand yet why at the beginning the so-called clusters, they grow more, reaches a plateau, and then eventually at large times it starts to deviate. Why specifically this?
Okay, so why it is like this? It is like this because you can imagine that if I have a landscape like this, so on short time scales I just see this minimum, and then on long time scales maybe I can explore a bit more. But if I explore a bit more, the correlation with the initial position decreases. So the mean square displacement increases. So I should go from something which is here to something that is smaller. Is it clear?
Can you interpret the plateau as a kind of measurement of flow dynamics of the system?
Actually, it's a measurement of what happens on fast time scales. If you go to long time scales, you start to see this structure. Okay? So you start to see how those minima are related one with the other. So the Q of x tells you how those minima are arranged in phase space. Okay. So this is interesting because it tells us that if I reach this line, this plateau is going to 1. Okay? So I need to find a solution for those equations, and I know that all the jamming transition is encoded in the behavior of these equations when Q is going to 1. Okay? Okay. I lost my notes. I lost my notes, but it's not important. Okay, so what we need to do is to study those equations when Q of x goes to 1.
What's lambda?
Yeah, okay, so lambda is a function that you can explicitly compute. I can give you the expression. So let me just write it instead of as a function of x, as a function of q, where I remember the expression. As a function of x, I don't remember the expression. So lambda of q is 1 minus qea plus so if I have the inverse function of q of x, I can compute this, and this is lambda of q. And then if I have lambda at a given q, I can get lambda as a function of x, which you can have an expression, but now I will not be able to derive it. Okay.
I'm curious about the fact that you have those complicated equations.
Mm-hmm.
And can you comment on the solutions of this? Because everything rely on that.
Yeah.
Is it stable numerically? How do you do that?
Yeah, okay, so the solution is a bit complicated. So I think that if you use some software of numerical, of symbolic computation, you can get a solution when you are far away from jamming. And the way in which you solve those equations is, okay, the way in which we did solve the equation numerically is that you go back to the original formulation in which you have KRSB. So the function q of x is discretized with a stair. And what you do is that you rewrite the derivation that I did for this equation. This derivation was a set of Gaussian integrals inside Gaussian integrals inside Gaussian integrals. And this you can do numerically. So there is a way to integrate. So what you do is that you have an algorithm. The algorithm is just simple. So if you want to integrate them numerically, you start from a guess of q of x. Okay. So you guess it. Then you compute the solution of this equation. So you start from 1 up to x equal to 0. And this gives you this function f. Then you plug this inside this equation. And you integrate from 0 to x equal 1, this equation for p. And then you use this equation to update your guess q of x. Okay? So you just do what's written in the equation. It's just that the only numerical problem is how you discretize this PDE. And these PDEs are complicated just because, I mean, if any one of you has worked with numerical PDEs, it's very complicated to handle them. So this is just because this is nonlinear and so on. Okay, so what we need to do is just to look at what happens when q goes to 1. Okay, so I would like to just see what happens from the SAT phase. Yes?
What are the minima in QX?
What are the minima in?
Maybe that plot over there, there is a free energy landscape or something.
What?
A free energy landscape.
Yeah, this is a free energy landscape.
No, in QX, what is the value of
This one?
Yeah.
Okay, so this one is, so if you take this model, you can look at, so you have a sphere that is the whole phase space, and then you have this blob of solutions, okay, and then this sides is this. So it's the farther I can go with two solutions. And instead, this thing is the ones that I found if I just move a bit around myself. So if I'm a particle at high pressure, if I start to move, I just see a cage. But then I can start to see that somebody is moving there, so I can move a bit more, and then I can explore the landscape. And here it's the same. So this value is just the size of the big blob. And this thing tells you the fine structure of the blob. So for example, here, this would be 1 minus QEA. Okay, so this is, the distance is, I mean, if I call this is, Q is not a distance, it's a co-distance, because if Q is equal to 1, the distance is 0, so I didn't move, okay? So the mean square, so, yeah, so this Plateau value is just the size of this, and in the glass, it's just the size of the metabasin of the glass, okay? Okay, so how much time do I have?
40 minutes
Okay.
until 1 hour.
So I think because I lost my notes, which is bad. And I don't want to say wrong things. So I can...
To have all this in mind, all those simple equations.
I can try. Wait. Yes, here it is. All right. So what you can show, so the first thing that I would like to tell you is that, so in this phase diagram, there is a line that separates a replica symmetric phase from this full RSB phase. So what does it mean that you go from a replica symmetric phase to a full RSB phase? It means that when you are here, this function Q of x is just a constant. Okay? What does it mean? It means that you just have this plateau and nothing happens when you go at long times, because you just stay at this plateau. Okay? When you cross this line, then there is this part here that starts to develop. And what you can show is that since you have this, you have a region here where if I compute Q dot of x, this is different than 0. Right? So if I have something that moves, the derivative must be non-zero at some point. So if I take these equations, in particular this one, I can take the derivative with respect to x. So this equation holds for all x. And now I take the derivative with respect to x. And what you get is that you get another equation that holds only in this full RSB region. That is the following. You get 1 over. Okay, so this is an integral over h. So this equation, you get, so you take this equation, you derive with respect to x, and then you get something like this. Okay, so you have something which is proportional to Q dot. So you can have two solutions of these equations. One in which Q dot is equal to 0. That's the replica symmetric solution. But you can have another solution in which Q dot is different than 0. And then automatically you get a new equation, which is this one. Okay? So this equation is what we say it's marginal stability. Okay? So indeed, it tells you that you have a way to interpret it is that, so if you look at those equations, you have a set of identities, and you have infinite many of them. for each x. Okay. Okay. So that's the first observation. And the second thing that I would like to discuss is the initial condition for this equation. Okay, so I erase this thing, which is just the Lagrange part of the action. So the idea now is that we would like to study those equations for q going to 1, that is the Jammine limit. Okay. So since I approach the Jammine transition from the satisfiable phase, which is the R sphere side, if I send the temperature to 0, this is just a theta function, right? Do you agree? So if I have, so V is just so if I send beta to infinity, this just goes to theta of h. Right? Do you agree? All right. Now, so this q of 1 is nothing but QEA. Okay, q of 1 is QEA. And this is going to 1. So you start to see that you have something strange happening because you have an integral, a Gaussian integral, with a variance that is shrinking to 0. Okay, so you can try to do some asymptotic analysis of this f of 1 and h. And what you get is the following. So this, when QEA goes to 1, it's roughly minus h . So if I plot this function, this is just, so I get 0 here, and then I have a parabola there. And then you start to see that, so this function is regular everywhere, apart this point here. But if I take the third derivative of this, I have some delta function. Okay. And so this may be bad because you see that those PDEs they take, I mean, in order to integrate them, you need to take derivatives. So having something that is not well behaved in some point may generate something in the PDEs. Okay, so this is really math, and I will try to translate it into physics. So this region here is the region close to h equals 0. But h equal to 0 is just the point in which you have, so if I take a gap that is equal to 0, this corresponds to spheres that just touch. So there is something when my cage size is going to 0, so the sphere cannot move, there is something weird that is going on in the limit in which two spheres touch, which is this region here.
A quick question.
Yes.
Can you make or just use a smooth version of the theta function?
Yeah, but then you will need to send the smoothing to 0. Right? So what you can do is that of putting the smoothing, that you say, okay, I take these PDEs, and then I study them for Q or for Q that is going to 1. And Q will be my scaling variable. Okay, it's not a scaling variable, it's just, sorry, not a scaling variable, but Q will be just a measure of the distance from the critical point, okay, which will make the smoothing. So at any Q that is not Q at Edward Anderson, this thing is regular. You expect that it's regular. So those equations are developing a scaling regime in this region here that is needed to smooth out this singularity. So I don't know how many of you have seen scaling regime in partial differential equations. Not many. But actually, it's interesting because I think that one of the first, not even application, one of the first discoveries, I think, of anomalous dimensions in critical theories was not in critical phenomena. It was in partial differential equations. So there is some work, for example, by Barenblatt, in which I just flash what the work is about. So you just want to study a diffusion equation for some function, u of x and t. So this is a diffusion equation. But now he says, he says that the diffusion constant depends on this. It's not a constant. It depends on the Laplacian. So it takes two values. So it's 1/2. I don't remember now, but it's the same. If this is positive, and 1/2 plus epsilon if this is negative. So it's a nonlinear PDE in which the diffusion constant is discontinuous as a function of the Laplacian. So if epsilon is 0, then this is usual diffusion, and you know that u goes like the time to minus 1/2. This you know. This is just diffusion. And now when you switch on epsilon, you start to see an anomalous dimension here appearing. And this you can compute. Okay, so this was known in theory of PDEs. And here we have more or less the same phenomenon. It's a bit more complicated because we don't have just one PDE. We have two PDEs coupled. But in the end, we will get something that is very close to this. OK, so how do you study those things? So you need to find a scaling solution for those PDEs. And this scaling solution tells you what happens when all this function is going to 1. So all this region is going to 1. So, OK, let me just describe the scaling ansatz with the scaling functions. So by the way, this scaling theory that I'm going to tell you was in a paper, was first derived in a paper with Charbonneau, Kurchan, Parisi, myself, and Zamponi. 2014. And it's the same for the perceptron. So perceptron and R, so this was derived for R spheres, but it's really the same in the perceptron. OK, so OK, why am I writing with the yellow one? OK, let me take the white one. Okay, so the first thing is that you need to define some distance from jamming. Let me call epsilon the distance from the jamming point. Okay, so this can be alpha minus alpha j, where alpha j is the jamming point, or sigma minus sigma j, or some combination of them. It's just a distance from the point where QEA is exactly equal to 1. And now I will just do something, but instead of looking at the function q of x, I prefer to work with the inverse function, that is x of q. Okay. So this is just because I would like to look at what happens when q is going to 1, and here it means that I have to take x going to 1. So it's a bit more, it's less easy to see what happens here, but here there is no problem. So what I claim is that the PDEs that are there admit the following scaling form when q goes to 1. So first, I define some epsilon of q, which is just 1 over epsilon x of q. And since x is finite, I expect that when epsilon diverges, when epsilon goes to 0, this diverges. Okay? So in particular, I expect that this, in this limit, behaves like some prefactor 1 minus q to minus 1 over kappa, where kappa is a critical exponent. And then, so I need to study what happens in this region. And then let me just write a scaling form for the function p of x, or p of q. So this has 3 scaling regime, and only one is universal. So I just write the expression, and then I comment. So when kappa is negative, I have some scaling form of this form that depends on this critical exponent kappa. Then I have an intermediate scaling form that holds when h is roughly equal to 0. So you have something for h negative, something for h that is roughly equal to 0, which corresponds to the point in which particles are touching. And then I will have something when h is positive, okay, which corresponds to positive gaps. And so you have, 1 minus q minus a over kappa. And then I have some scaling function of h over root 1 minus q. And this is when h is order of root 1 minus q. So since q is going to 1, h is going to 0. So this means that I'm in this regime. And I just zoom in on this point with a length that is 1 over square root of 1 minus q. So what I'm doing is that I'm just saying that this function here will have some, okay, so this is f. But p, in the same region, will have some scaling form, some scaling function, precisely as the one as Jim was discussing about. Okay? And then I will have something.
Francesco, can you quickly remind me of the gap distribution and the force distribution that you had at the beginning?
Yes. Okay, so what you can show is that when Q goes to 1, this function here gives you the distribution of forces and gaps. So this came as a Lagrange multiplier, but it has a physical meaning. So if you can take your free energy and then look at the distribution of gaps and forces, starting from the free energy. It's simple to, if you know the free energy, you know the distribution of gaps and forces, and you do the computation, and then in the end, this distribution is encoded in this P of Q and H when Q goes to 1. So this scaling form is important because it gives you the form of gaps and forces.
And the 0.4 will come out of it.
Exactly. So you have 3 regimes. One when H is negative. So H negative, this will correspond to forces. So this P minus will be the distribution of contact forces. Then you have something for positive H. This will be the gap distribution, related to the gap distribution. And then you have something in between that needs to match forces and gaps. Okay? So the two are related. And we know that they are related because there is a scaling relation that was derived by Mathieu Viard. But then we can do more than derive the scaling relation because those two are related through this matching regime. And this matching regime will obey some differential equation that we can obtain by just plugging these ansatz into the PD. So this is a scaling form. I can take it and plug it in the PDE. And this will give me a scaling equation for this matching function. Okay? And this matching function is the one that allows me to go from gaps to forces that are related, needs to be related. Okay. Okay, so this scaling form depends on this critical exponent kappa and another critical exponent A. Okay, so we need to find a way to compute them. So let me just give you the physical interpretation for this exponent K. So if you assume, so if you look at this scaling function for y of Q, this tells you that QEA is going to 0, sorry, is going to 1 as 1 minus some constant epsilon to the kappa. So you have your cage size is shrinking to 0 with a power law. And this power law is controlled by this kappa. So if you think about particles, you should have that delta EA as a function of the pressure. When the pressure diverges, is shrinking to 0 with a power law. So this should go like P to the minus kappa. And since P, the pressure, can be taken as a measure of the distance from the jamming point, I can just morally think about P as epsilon. Okay? And this is something that was first, I think, seen by Carolina and Mathieu Viard, that you have this delta A, and this was, I think that in your paper you say that it was close to 3/2. Yeah. And it's close to 3/2, but not exactly 3/2. Okay.
And a very small system.
And very small system, so. Okay. So you can, okay, so this is the scaling form for P. And of course, you have another equation that is an equation for F. And again, you need to look for a scaling form for f when h is small. Okay, so this you can do. And I just write it, but okay, so this I can erase. So what you get is, okay, so you can define this variable. Okay, now I just, okay. So I just define this. And then I claim that this has some scaling form when q goes to 1, which is minus root of 1 minus q, and then I have a scaling function of h divided by root 1 minus q. So I have a scaling function that lives in a scaling regime that is precisely this matching regime. Okay? So I just defined this function that is just a derivative of this function f, rescaled with this lambda of q. It's just some technical thing. But in the end, I will have that this function f is described by a scaling function, and this is a function of a scaling variable. Okay, so this holds when h is of the order of root of 1 minus q, and q is going to 1. Okay? Now you can study those things, so those scaling functions, and you can plug them in the PDEs, and you get two equations, one for m, and another one for P0. So the one for m, let's see if I have it or not. Yeah. So what you can show is that this function m satisfies the following ODE, so it's an ordinary differential equation because this function is a function of just one variable. So you have m of t minus t m prime of t is equal to m second of t plus 2 k minus 1 over k mt 1 minus mt prime. So this is an ordinary differential equation, second order. So you need two initial conditions. And the initial conditions are fixed by the boundaries. So you can show that m of t is 0 when t is much larger than 0. So when h is going to infinity, and goes like t when t it's much smaller than 0. So you have two asymptotic behavior for this function. And if you fix k, there is just one solution of this equation. So you have two boundary conditions. The equation is second order. And if I fix k, if I knew k, then this has just one solution. So imagine that I know this solution as a function of k. Now I take this, and then I look at the scaling form for p. I take it, and I plug it inside the PDE, this one, and I get an equation for P0. Which is, again, an ordinary differential equation, because P0 is just a function of a scaling variable. And I can just write it this way. So note that P0 is a function of the same scaling variable as m. Okay, so these two scaling regimes will talk to each other. So this is not very difficult to get. You just need to take this, plug it here, use that T is this thing, and take the leading terms. So for example, if you look at this term, you have P times M. M is morally F. And here you have P times F prime. So M was F prime. So this term comes from this term. This is just morally connected. So if you just do the computation, you get this. And you can show that this must be solved. Again, it's second order, because this is second order. And it must be solved with some boundary conditions that you can work out. And so you get that when T, OK. So when T, yeah. So it goes like this, T to the minus gamma, when T is much larger than 0. And T to the power theta, when T is going to, OK, it's much less than 0. So what are these two exponents? So you recognize that this is, so since when T is positive, I'm looking at the gaps. This should give me just the power law distribution of the gap, the power law of the gap distribution, which diverges as T to the minus gamma. So you remember that at Jammine, we have that the distribution of positive gaps has a divergence when the gap is going to 0. So this is H, and this is G of H. And I told you that this P0 has a part that needs to interpolate with the gaps, and another part that needs to interpolate with the forces. So this part is just the one of forces. So this should go like F to the theta. So this P0 encodes for both behavior, gaps and forces. And this theta and gamma can be related to the exponents A and kappa. And I just write the expression. This is 1 minus k divided by k over 2 minus 1. And gamma is 2A over kappa. So if you know A and kappa, you get access to the critical exponents for forces and gaps, which control all the jamming point. OK? Good. So let me just look at this equation. So if I have a solution for M, and I fix K, then this equation still depends on A. Because I have two boundary conditions, but A is still unknown. OK? So what you can show is that, so the second comment that I would like to make is that you see that this is a kind of eigenvalue problem. Because you see that A is just multiplying P. So if I look at all the rest as a kind of operator acting on P, this is like an eigenvalue. But it's a nonlinear eigenvalue because the operator itself is nonlinear through the boundary conditions. So you get that those exponents are the solution of what is called a nonlinear eigenvalue problem. Precisely as in this case. It's just that it's much more complicated. And now the thing is that how do you fix A and K? So if I fix K, there is only one eigenvalue that satisfies this equation and both boundary conditions. So if I fix K, I have just one solution for A and P0. Okay? So I need another equation for K. And this you get because I told you that we had this relation that was holding just in this full RSB phase, that was this marginal stability relation. If you take this relation, you take another derivative, you get an additional equation that I will write here. That tells you the following. So you get that k minus 1 over k is equal to 1/2 the integral of P0 of t So remember that m was f prime. So m second, it means f third. And you remember that this function f had that discontinuity in 0. So you need the scaling function to smooth out the discontinuity, and that's where it comes in. And then you have m prime of t squared So, to summarize, so if we fix k, we get a solution for this equation, for m. And we also get a solution for a and P0. Now, knowing P0 and knowing m, I can plug them here and get k. So this closes the system. Okay, so how do you solve for those critical exponents? What you do is that you take this equation, you integrate it, fixing k, you get this P0, and then you update your guess for k from this equation. Okay, so these are all ODEs that can be solved simply numerically. And so if you do this, you get the values of the exponents. So you get that k is equal to 1.41474 something. And theta is equal to 1.42311. And gamma is 0.41269 something. Okay. So of course they are not rational numbers, and you see how they come out. I mean, they just come out from a nonlinear eigenvalue problem. Okay, for these sets of PDEs. Okay. So the last 2 minutes, I just would like to say that all those things are very important because, so as we said, they control avalanches close to jamming or at jamming. So why it is so? Because, okay, let me just make a last comment. So these are the values of the exponents, mean field exponents. And what you can show is that you have a relation, that this marginal stability relation tells you that when you go at jamming, if you look to the distribution of gaps, so you get a Dirac delta in 0, and then this power law. So what is this Dirac delta? This is telling you that when you are at jamming, you have a certain number of gaps that are exactly equal to 0. So these are contacts, right? So if I take particles, if their gap is equal to 0, they are contacts. So what is the weight of this delta? from the marginal stability relation, you get that the weight of this delta is 1. What does it mean, 1? Is that if I look at how many gaps I have, okay, so if I look at how many gaps I have in this delta, they are just n. So I have n degrees of freedom, m constraints, but precisely at jamming, I have n gaps that are exactly equal to 0. So I have that the number of degrees of freedom, that is n, is equal to the number of contacts. So this is isostaticity. And you get it from the solution. So in the end, you get isostaticity and the critical exponents for the transition. Now, the very last comment is that, so those things control the physics of these systems. Why? Because if I look at a packing, and imagine that I start to shear it. So I am at jamming. I have R spheres, so I will have some contacts with some forces. If I start to shear this thing, I will modify the contact forces, right? Because if I apply some boundary conditions, the force network will change. So at 0 strain, I have some force network and some forces with a probability distribution that has this behavior here, and here it's controlled by this exponent. So this means that if I shear it, this, you have to imagine that this is just the histogram of all the forces that I have. And in particular, let me look at the ones that are here. So if I shear the system, at some point I may have that the smallest force, which is the one that is changing a lot because it's already small, the smallest force can become negative. But if a force is negative, it means that two spheres are opening. So I have a gap that is opening. But if the gap is opening, the system is not isostatic anymore. So it will flow along a floppy mode. So what is the size of the smallest force? Well, since it's really the smallest, I can use extreme value statistics. And I can say that this is so the smallest force satisfies this thing, just because the smallest one is the first one in this histogram, okay, which tells you that F mean is of order n to the -1 plus theta. So this tells you that as soon as you apply some strain that is very small and scales this way, you trigger an avalanche. Okay? And why it's an avalanche? Because essentially, since the floppy mode is typically extended, you can have also floppy modes that are not extended, but let me forget. They are not very important. And in the end, they are suppressed in some regimes. So you will have a floppy mode that extends all over the system. So you can get a big rearrangement of the system. And you can compute the scale of the rearrangement, so the size of the avalanche. And the size is controlled by a critical exponent that depends on the critical exponents that I wrote here. In particular, the avalanche size is controlled by a critical exponent that is 2 over k. And this was computed by Franz and Spiegler. I think 2017 something. So this is just to say that the physics of these systems is really encoded in all this. And from numerical simulations and the the best estimate, numerical estimates in simulations of these exponents is in a recent work by Charbonneau et al., 2021. So you don't see any reasonable deviation from these values. So this mean field theory that we derived in the perceptron, but it's the same as our spheres, gives access to essentially to control the physics of these packings at jamming. Okay, so I would like to conclude and thank you, Danilo, Carolina, and Itai for the very kind invitation. It was a pleasure to be here. I would like also to thank the support of the Institute. Really did a wonderful job. And thank you all for the attention. If you have questions, don't hesitate even to write me. I will leave on Saturday. But if you have questions, you want to know more, just write me. OK? Thank you.
We would like to thank you, Pierfrancesco, for those very nice lectures. But before, let me then, we have questions.
So how much of this calculation relied on approaching the jamming transition from the SAT phase versus the unsat phase?
So the unsat phase is a bit different in the sense that here you have a different scaling regime. So what you have to do in the unsat phase is that you first need to send the temperature to 0, because I mean, this phase diagram is at 0 temperature, right? So there is no temperature here. So if you send temperature to 0, then you look at what happens in this limit, and this will give you a scaling regime, a first one. And then this scaling regime has a crossover to this scaling regime when you approach the transition from this side. Now, the scaling regime that you have at 0 temperature really depends on the potential, so on how particles interact. So if you take, for example, particles interact with an harmonic potential, you get a scaling regime. If you take particles that interact with a linear potential, what you get is that this scaling regime extends all over the jammed phase. Okay, so if you take V of h, that is absolute value of h, theta of minus h, so you pay some energy cost that is just linear in the gap. What you can show is that you have a scaling form for the solution of these equations. The PDEs, the original PDEs, are exactly the same, but the scaling form is more complicated. So you have like 5 scaling regimes. 2 of them are universal, so they depend on these functions P0. Actually, you have 2 functions, P0. You need to work them out. And then they are related by a symmetry. And this symmetry tells you that, in the end, you have the same critical exponents as a jamming. So this jammed phase, in this case, is as critical as jamming. So you have isostaticity above jamming, and all critical exponents are the same as a jamming. And this is important because when you approach the unsat phase, in this case, this is very different from what you get if you have harmonic spheres. For example, if you look to the scaling of the number of contacts, number of overlaps, and things like that, this is very different from harmonic spheres. So the typical scaling, for example, of the number of overlaps, this is scales like the square root of the distance from the jamming point. And this changes when you take this thing. So this is really, this affects really the property of this phase.
OK, thanks.
Oh, nice. Then it's, we had the numerics for this before all the theory. So this clarifies things.
Yes, I'm sorry. Yes, so
Yeah,
these critical exponents were measured. So you first had a measure of this that was close to 3 over 2, and this is close to 3 over 2. And then there was a series of papers by Matteo Villar, Idan Lerner, and Gustavo During looking at gamma and theta, and then at the same time there was Charbonneau, Parisi et al. That were measuring those exponents, and then the problem was how to compute them. And so this was first done for large dimension, and then I just told you the story in the perceptron, that is the same, just to have something which is simpler.
Very nice. So is there any very fast question? Okay. Let us close with that, because then we have to come back for the last lecture of today.
Just a quick question. Can you estimate the minimal shear stress that you need to apply in order to start
Yeah,
average?
this.
Oh, okay.
So it's just controlled by this theta.
Okay, thanks.
Okay, so let us thanks again, Pierfrancesco, for this very
Thank you.
nice set of lectures.